recently joined Saha Institute. Um, so Saha Institute of Nuclear Physics, and a brief thing about his background. He finished his PhD from Video Owners Group in Tohoku University, and subsequently he was there first as a postdoc and then as a research assistant professor. And his interests are mainly in the area of spintronics. And today he'll be talking to us about his more recent interest, which he wishes to pursue again here, spin-orbitronics with metallic antiferromagnets.
Thank you very much. It's a very great opportunity for me to be here and to present my work.
Can you hear him?
Can you hear? So I joined SIMD in August and trying to set up my lab and trying to keep the research running. So as Priya said, this is a brief background of me. I did my PhD in 2016 and subsequently was a postdoctoral fellow there, research assistant professor, and then I joined the SIMD. And during this time, my research was funded by several grants from JSPS and also from the university itself. So I would begin my presentation by just asking a question: that what are the gadgets we use in our everyday life? So if we look around us from the morning to evening, then we see that we are using a lot of different electronic gadgets, and they have become an indispensable part of our life. But if we look at them closely, then we realize that all of them actually utilizes the charge property of the electron for its function. But however, these charge-based electronics, or the VLSI or the LSI, they have some shortcomings, or they have some roadblocks for their for to address in future, which is mainly related to the further miniaturization of their size, the huge amount of power consumption that they that they have inevitably, a problem with the processing speed, and also a difficulty to realize non-conventional architecture. And that is one of the reasons why we want to have an additional alternative. And in my research, which you know that there is another field of research which also utilizes the spin degree of freedom of an electron along with its charge, and that is called the field of spintronics. So I work in the field of spintronics, and mainly my work tries to understand the fundamental relativistic of the quantum mechanical interactions and try to show a new paradigm for the establishment of the future development. And the question is, how do I do that? I mainly try to understand the conversion from an electrical charge to spin angular momentum or orbital angular momentum, and study the effect of this conversion process under the application of temperature, light, or electric polarization, which basically means currents. So today I would mainly be talking about this, uh, technically this three things. The first is spin conversion, which is called spin effect, and which gives rise to a torque, which is called spin orbit torques. Then I would talk about spin orbit torque in antiferromagnets and how you can use this non-equilibrium current in these torques to manipulate an adjacent ferromagnetic layer. I will show you that you can even use them to manipulate an antiferromagnetic system, and also you can use them to manipulate spin textures embedded in antiferromagnets, which are called Stern. Okay. So let me first begin by just giving you a brief idea of what I mean by this charge to spin conversion or spin orbit. So very simply speaking, if you take a heavy metal with a strong spin orbit coupling, for instance, it will be platinum, tantalum, tungsten, etc. If you pass a charge current, then that charge current would give rise to a transverse accumulation of angular momentum across all the four different phases of the momentum. So here I have just shown two of them, but all the four phases will have spin accumulation with different spin angular momentum. And then you see that there is a transverse flow of spin angular momentum, which is called the spin current, and this ratio of the spin current to the charge current is called the spin Hall angle, which is basically the efficiency with which you convert the charge to spin. Now, when you have, so apart from that, there is also another effect which coexists along with spin Hall effect in most of the systems, and that arises from an uncompensated electric field across the interface. This is mainly called the Gauss-Weissenstein effect. But the point is that the net consequence of both of these effects are more or less the same, where you have an accumulation of spin angular momentum at the interface. So now when you have a ferromagnet or an antiferromagnet on top of them, this spin angular momentum can be absorbed by the magnet, and then it can give rise to torques acting on the magnetization. So this is called spin-orbit torque. So you apply a current, and this electrical current exerts a torque on an adjacent magnet. And this spin-orbit torque can actually give rise to, it was understood that if it is strong enough, it can actually cause reversal of this magnet. But there are several questions which needs to be answered, like what is the dynamics of the switching, how fast we can switch. These are the questions which we wanted to address. So before going into the specific problem that I will show you, this is how one slide on how we grow our samples. We mainly use a magnet of sputtering. This is more or less the specs that I used to have back in Japan, and we also have a sputtering here in our group in SAMIK, and we can also grow with inputs. And this is roughly a cross-sectional clear image of a sample that I would show you the data of. This is a polycrystalline sample which is grown on silicon and which has the several different layers of tantalum, platinum, manganese, ferromagnet, and cap. And what we actually do is we first grow these samples by sputtering, and then we use photolithography. Most of the part we use photolithography, and for some experiments we also use electron beam, and we then use argon ion etching or argon ion milling techniques to fabricate devices, and then we measure the transport under the magnetic field or the radiation. So this is basically the workflow that we generally have. So the first question that we actually asked way back in 2016 is, can the spin-orbit torques induce a reversal of an adjacent ferromagnetic sample? So this is the stack structure that we used for our experiments. It consists of a tungsten layer, and it has then a ferromagnetic overturned boron, and then an NGO and a tantalum cap. So this was grown by sputtering and then subsequently annealed. And this annealed, after this annealing, we get perpendicular magnetization of the overturned. All the grown systems which were not annealed, in our case, they have an in-plane. So this is the device that we made. This was made using photolithography, and this is the measurement scheme. So what we actually do is we first saturate the magnetization out of the plane of the board by using a magnetic field, and then we pass an electrical current, and we detect the direction of the magnetization by using anomalous Hall effect, which is the transverse voltage in this joint. So this is our experimental result. So we measure the anomalous Hall resistance as a function of the current which is flowing through the channel. So starting from a down configuration of magnetization, as we sweep the current, then we see that we can deterministically switch it from down to up, and we can also do it from top to down and vice versa. And this experiment was done with a DC current. So if we apply an electrical pulse, we showed that we can reproducibly switch it down to 10 nanometers. So this means that the spin-orbit torques definitely can switch the magnetization of heavy metal ferromagnet joint. But the question is that also, as you can see here, we need to have an applied in-plane field in order to have deterministic switching. So the question is that why do we need this in-plane field? And the problem is, can we actually eliminate the requirement? Because this is not a practical from the point of view of device application. So to understand why do we need the in-plane field, we can look into the Landau-Hilbert equation of motion, which defines the magnetization dynamics under the application of the electrical currents. So this is how the equation looks like. The first term is the precession under an effective magnetic field, and then we have the damping, and the third and the fourth term are the ones that is coming from the electrical currents. And we can do this simulation in a micromagnetic simulator. Any one of them which is given in the
coming from the these are the magnetization.
Yeah, these are the torques that are arising when you inject the current in the field. So this electrical current is giving rise to a spin angular momentum in this, and this spin angular momentum is absorbed by the magnet, and that gives rise to torques. And these torques can be of two types, which is defined like this.
M is the
M is the magnet.
magnetization of the
Yeah. So if we do this calculation, then it is seen that these two types of torques, they do not cause a deterministic switching of the magnetization. So this first type of torque, which is called transistory torque, that only has a rotational motion of the magnetization. So this has a rotational symmetry, which means that if you start from this top position, the magnetization will go on rotating along this plane as long as the current is applied. And for the field-like torque, it produces a canting of the magnetic field. So when we are switching from up to down, in that case, that deterministic reversal cannot be applied, cannot be obtained only with these torques. When we apply an in-plane magnetic field, the magnetic field actually breaks the rotational symmetry of this torque, and then you have the deterministic switch. So that is the reason why you need this external magnetic field to have a deterministic the magnetization. But the problem is how to overcome the obstacle of this external magnetic field during the spin-orbitronics switch. So the yeah, that's what I was going to show. So before our work, actually, people tried to break this rotational symmetry by several different techniques. I would just list two of them. The first is they took an island. So this is a nanomagnet. This is a cobalt platinum layer, and they basically made these lithographically patterned magnets along these two sides. And these lithographically patterned magnets were a source of in-plane magnetic field. And this in-plane magnetic field then broke the symmetry and it gave rise to the deterministic. And another way people did was they used interlayer exchange coupled magnets. So in this case, they had this cobalt iron layer which has a perpendicular magnetization, and they exchange coupled it to another cobalt iron layer through a ruthenium spacer. And this interlayer exchange coupling was a source of magnetic field that broke the rotational symmetry. But however, these is very challenging in terms of the fabrication point of view, and this is also very challenging because you need to have the right thickness or adjust thickness so that you can basically get a considerable magnetic field to break the rotational symmetry. So we tried to have a much simple alternative, and the thing that we thought of was to use an antiferromagnet bilayer system. So we were actually the first group who actually showed this. So our idea was that we know that an antiferro-ferro bilayer system has an inbuilt magnetic field at the interface arising from the exchange wire, which we already know. But however, at that time we didn't know whether the antiferromagnet itself could also be a source of spin-Hall effect. So the idea is, if this antiferromagnet is a source of an exchange bias field and is also a source of spin-Hall effect, then using the same system, you can solve the dual purpose. It could be a source of spin-Hall and it could also be a source of magnetic field, and then you can, in principle, have field-free switching with this bilayer kind of system. So that was the idea. So what we did was we looked into the literature of what material we can use, and we found that there is a very well-known material which is an alloy of platinum and manganese, which have been used by the industry for a very long period of time for a different purpose, of course. But they can be very easily grown. They have a nail temperature above room temperature, and they have a very simple press-centered tetragonal structure, and can be very easily grown with sputtering. So we took this material and we grew this pimples by sputtering. And in this case, the thickness of the cobalt iron boron was such that the magnetization is lying in the plane. It has an in-plane z-axis. And this is a magnetization versus field at room temperature, where the black line is the data when you apply the magnetic field out of the plane, there is in this direction, and the red one is applied along the plane, which is this direction, which means so from here you can actually see that the easy axis is in the plane, and you also can get the anisotropy field roughly from this point. And we also did some more characterization. For instance, the energy dispersive extra mapping to see that there is no significant intermixing or interdiffusion of the different layers. So here you can see the elemental mapping of tantalum, platinum, manganese, and cobalt. So you see that there is no significant diffusion between any one of the layers. So what we wanted to do was, because we have two questions. The first is whether this antiferromagnet is a source of spin Hall effect. That we have to clarify first. So we first tried to investigate the strength of the spin orbital in the system by a technique which is called harmonic Hall measurement. So there are actually various kind of techniques that you can use for harmonic measurements and for the spin orbital quantification. And one of them is called the harmonic Hall measurement. The advantage is that this is a transport technique. So you can just make a device. A big one also is okay. It doesn't necessarily have to be 10 microns. It can be 50 microns or 100 microns. Just take 4 contacts and put it in a PTMS or any other machine and just measure. So use this technique. We made these hall bars with photolithography. They're pretty big devices. And what we actually do is the following. So we first saturate the magnetization. The magnetization is lying in the plane. And we apply a magnetic field. We rotate the magnetic field in the plane of the sample. And what we measure is, we measure this transverse voltage, but we measure the first and second harmonic voltage. The first harmonic resistance, actually, if you work out this equation, that corresponds to the planar Hall signal coming from the magnetization. And the second harmonic resistance actually contains information from this current induced torques, as you can see in this coefficient and also in this coefficient. So if we measure both the first and second harmonic, and if we know this Lehner Hall, anomalous Hall, and all of these terms, then one can actually evaluate the effective field or the effective magnetic field that is coming out from this application of the electrical currents or the spin. And then one can actually define a parameter which is called the efficiency of the spin orbital, given by this formula. So this is our experimental data. So this is the first harmonic resistance as a function of the magnetic field which is rotated in the plane. This phi is the angle between this x direction, which is the direction of current, and the magnetic field. So this follows this kind of a behavior, which roughly follows the sine theta. And this is how the second harmonic looks as a function of phi. The interesting thing about the second harmonic is that the second harmonic not only gives you the current induced torques, but looking at the sign of this voltage, you can also get an idea about the sign of the spin Hall angle. So for here it's positive, and if it's the opposite sign, then this will become zero. So it will immediately tell you what kind of spin Hall it is. And then we did this same experiment by varying the magnetic field. So this is for 300 millitesla, but we did it for various different applied magnetic fields. And then we can plot this curve. This is basically this the coefficient of the first term as a function of this external field. And the slope of this graph actually gives you this effective field which is coming from the. So we can also do the same thing for the field like torque, and we quantify both of them. So finally, after getting these effective fields from the currents, we can define this parameter xi, which is the efficiency of the charge to spin conversion, and then we can plot it out as a function of the thickness of the antenna. So what we see, first of all, is very interestingly that definitely the antiferromagnet is a source of spin Hall effect. And also concurrently, several people other than us, they also quantified it by using other techniques. And we can then fit this Slonczewski-like part, this blue data by this equation, and we can find out the effective spin Hall angle, which is roughly roughly 0.085 and a spin diffusion length which is around 2 nanometers per lambda.
The U beta is going upwards, whereas what we give deadline is going down.
This part you mean?
Yeah.
Yeah, we actually think that in this portion there is probably contributions of the spin Hall effect also from the under layers and probably from the maybe from the interface. So this model actually works only for when you have bulk type behavior.
But rest part is flat.
Yeah, once you go above this 4 or 5 nanometers, also the antiferromagnet is becomes very disordered when you make it very thin, below 5 nanometers or more.
Consider the integration between transfer.
We didn't calculate the international transparency in this case, but I believe that there is a contribution from the
Because
information.
you have to line when
Yes,
the
yes,
spin transfer, not all the
yes.
transfer.
Yes, yes. I do agree with you. But during this point, at this point of time, we were, because we did this exact technical concept, we just considered the bulk. And then what we did was, so this indicates that the antiferromagnet could be a source of spin Hall effect, which is an important information to have. And then what we can do is we can plot this spin Hall angle for the various different components of this manganese-based antiferromagnet family. So if you take these several different members, starting from iron manganese to platinum manganese, this is our data. And then you also take the different data available in the literature, you see that there's a clear trend. And the trend shows that depending on the spin orbit coupling of this non-magnetic metals such as platinum, iridium, there is an increase in the spin Hall angle. So the more spin orbit coupling is of this non-magnet, the more spin Hall angle. And also, we compare our experimental data with the first principle calculation, which is shown as the red circles, and the spin Hall conductivity, which is calculated from our experiment, and the theory roughly matches. So this indicates that in this system, the spin Hall effect is mainly originating from the spin orbit interaction or the spin orbit coupling of platinum. So platinum is the major contributor to the spin Hall effect in this antiferromagnetic.
Scale with the resistive.
Sorry.
Scale with the resistive.
So for this case, we observe that it's mainly coming from the intrinsic spinning curvature. Yeah, but basically we just compare the magnitudes coming from the intrinsic points, and that's all.
How are you for sure? Scattering, purity scattering.
There could be contribution from the impurity scattering, which is probably we have a difference. But our the motivation of this work was to find out whether this antiferromagnet has is a source of spin Hall angle or shows spin orbit torques. So that is why we compared our experimental data with the first principle calculations, just considering the bulk spin Hall.
Till now, you have been discussing more about the classical picture, this equation. But suddenly, you are talking now about the very curvature.
So that is the origin of the spin Hall effect, or the intrinsic component of spin Hall effect.
Yeah, but classically, there is no very.
Classically, there is no. So what? So from my understanding, what happens is when you have a spin orbit interaction in the system, the spin orbit from the spin orbit Hamiltonian, if you calculate the velocity of the electron, then the electron velocity has first term which corresponds to the straight flow of the electron, and then another part which comes from the rate curvature, which basically separates out separates out the electron depending on the state, and that term comes from the rate.
The very curvature, you see the expression for the resistivity is connected to very curvature. For electron flow, electron resistivity MLS. You can directly tell. I don't know what exactly will be happening if you have an MLS behavior spins. Okay. Electron flow and spin flow are not same,
No, they are not.
right? So, is there any derivation for that?
I'm not so familiar with if there is any derivation. Uh, but these have been calculated considering the volumes and all of that, which originates
From the
from the intrinsic part of the spin.
intrinsic. Okay. Because you see that the whole Bailey curvature funda comes because there's the electrons moving in effective magnetic
Yes,
fields at
yes,
quantum.
yes, yes.
Here I'm a bit more confused because initially you dealt with the classical, now you're jumping to the quantum mechanics, right? And this expression I am not aware of. So
Okay. I might have something to show you. I'm not sure it is. It will be of these. Okay, so in crystals, actually, the so this is the usual spin orbit interaction Hamiltonian. And in crystals, when you have a periodic potential, then you can actually write this in this way. So I have actually borrowed this from these papers. And then this is the magnetic field probably that you are talking about. And then if you solve these equations for the electron velocity, then you get this term which corresponds to the straight motion, and this term which is deflecting them separating.
yeah, that's for the electron motion.
Yeah,
That's for the electron motion.
yeah,
Then you are talking about the spin current
yeah,
because here you have like localized moments also, right?
yeah. So the electrons are separated out, like the spins with opposite polarities are separated out, and because of spin Hall, and then they are absorbed in the magnet, right? And then they are exerting the torques on the magnetization.
I think let's talk
Okay,
first.
okay.
We can discuss this.
So what is the D of K in this? An expression you showed just now.
I think it's the effective magnetic field at the at the
Yeah. So that is just like your mu dot B then.
yeah, that's a mirror.
Yeah. So but the, so just your Zeeman term.
This is Zeeman. Okay, so so once we established that the antiferromagnet could be a source of spin Hall effect, then we wanted to go to the next question, that whether it can be used to reverse the magnetization of an adjacent ferromagnet. Now, many of you can ask me that if you look in the slide, you see that we have changed the ferromagnet. Previously, the ferromagnet was cobalt iron boron, and now it has suddenly become something different. It is because we were not able to get a perpendicular magnetic easy axis with cobalt iron boron for some reason. So we had to change the ferromagnet into a different one. And with this ferromagnet, we were able to get a perpendicular magnetization. Even though we would like to have cobalt iron boron with a perpendicular magnetization in the system, it didn't work out for us. But then we subsequently succeeded in stabilizing these stack structures on silicon, and here the magnetization is actually pointing out of the plane, which means that one can basically measure or one can actually quantify or qualitatively understand the orientation of the magnetization by using an observer's function. So this is our magnetization curves at room temperature. So you can see that the red curve is the one where we applied the magnetic field out of the plane of the sample. So you see that it has a magnetic easy axis along this direction. And the blue and the green curves are the magnetization when the field is applied in the plane along two orthogonal directions. And here you see that this green curve, it shows that it has a shifted hysteresis loop, which means that there is a presence of exchange bias. And this exchange bias field is roughly 10 millimeters. So if you are working with polycrystalline samples, in my experience, roughly you get around 15, maximum 15 to 20 millimeters of exchange bias field in these structures. And if you work with epitaxial films, then there might be a possibility that you can get it. But this was sufficient for our.
So in these cases, you know it's well known that there is no error bias means so this
Exchange bias, yeah.
exchange bias. So is it because of the interaction between the layers? Is that
It's because of between yeah, I mean the coupling between the ferro and iron.
so effectively you are treating as a bias.
Yes.
But
Why do you need the capping layer?
Actually, MgO is hygroscopic, so it absorbs water. So and you also need MgO to have a perpendicular magnetic anisotropy. But if you keep MgO as it is, it will start absorbing water. So you cap it up with something which doesn't kill you.
How do you make the contacts there? With the top of the capping layer, you make the contact? Okay, you showed it.
No, actually, what we do is that you first made your your device, and then in the same ion milling where you are using to etch your sample, you can just etch it a bit more when you are doing the patterning for your board or your contact pads, and that will basically just remove these things, and then your metal will actually get exposed, and you can deposit high board or strong board.
sorry, I hope you don't mind.
No, it's perfectly fine. Yeah.
I mean, see, this cobalt nickel, other one,
Yeah.
mostly lattice mismatching because heat. So is that the layer are disordered and the interface is disordered?
This is, I think, so these are very thin layers. So, in my understanding and experimental observations, this probably forms an alloy because this is like zero point 0.3 to zero point 0.4 nanometers, and this is 0.6 to zero point 0.7 nanometers. Okay, so even when we do transmission electron microscopy, we cannot identify the individual layers because they are probably not even one monolith. But I think they form an alloy. And the only reason why we use that is because if you use this particular cobalt nickel reputation, it becomes easier to tune the magnetic anisotropy. Depending on the reputation and the number of stacks, you can actually control the anisotropy depending on your requirement.
How do they know that this is copy or the disorder in this?
No, the magnetic anisotropy. Yeah. That you can measure from here.
This is your polycrystalline.
This is polycrystal.
Then how do you magnetocrystalline anisotropy is related to crystallographic direction?
This
Huh?
interfacial
This is
perpendicular.
Huh.
Interfacial perpendicular.
But this is something yeah, interface here.
When you say that it forms an alloy, then sharp interface.
But we have never seen this different interfaces from the TEM. So
Usually because of the magnetization.
yeah, yeah,
Magnetization.
yeah.
You have the electrical
Yes.
they cannot complete alloy.
Yes, but experimentally we don't have an evidence for this.
Very well known.
Yeah, it's a very well known system. Yeah. But from the TEM we have never seen very good, completely.
Probably the resolution.
Maybe.
See, that's the reason I'm asking.
Okay.
You are talking about thin films.
Yeah.
And even if your one or two thin layers
Yeah.
are gone, I mean, basically
Yeah.
because of their lattice mismatch, how do you consider everything as a very smooth fit? No more.
We have
So basically, what you are getting averaged, sort of average magnetization or average.
I mean, I guess when you have actually you have pretty much an epitaxial.
this is the polycrystalline.
Now on your PT layer,
Yeah.
so would it be epitaxial on that? I mean, the lattice parameter of this.
Uh,
I mean, I think the discussion is about the alloy associated with this, right?
Yeah. Yeah.
With the CONI
Yeah. Yeah.
thing, right? So I mean, whatever it is, but is that epitaxial on the platinum?
I don't think it's completely essential.
How many how thick is it?
This is actually zero point 0.3 nanometers, which is 0.6, and they are just repeated
Okay, okay. In that region,
in that.
If it is polycrystalline, how do I understand the difference between X and Y? It's a little bit of difference.
No, this is just like this X and Y is just based on the convention of the samples.
Still
So
you see a difference, which is
yeah, and this
difficult to
difference actually this green curve that you see, this exchange bias that we see, that is around the direction where we have actually annealed the sample. So the magnetic field that was applied during annealing was along this particular direction.
Another thing, if the effect is interfacial,
Yeah.
then this is highly localized phenomenon. So film has to be very thin, otherwise the bulk property, how can you observe? You understand my point?
Yeah.
The magnetic field that you are saying this is an interfacial effect.
Yeah.
And if it is interfacial effect, then how will it affect the bulk, or the effect is just interfacial?
Well, I think that
When you are measuring Hall and
for the hall, it is.
oh, that is not that part.
Yeah. Yeah. So then what we did was we basically made the same type of devices called bond devices, and now we don't. So based on the experiments that we have, we don't need the magnetic field based on the concept that we want to show. So what we did is we first initialized the magnetization of this area by applying an out-of-plane magnetic field or current, and then we just sweep the current along this direction. We don't apply any magnetic field for this experiment. And this is our experimental result. So starting from the down direction of magnetization, as we sweep the current, we see that the magnetization goes from down to up and then comes back. And but more interestingly, we see that there are two things. First is without an applied magnetic field, we can switch the magnetization. So the requirement of the external magnetic field is not has been eliminated. And secondly, we also see that there are multiple resistive states that can be stabilized here, which is generally not seen in other ferromagnetic bilayer systems. So this actually led us to propose that with an antiferromagnet ferromagnetic system, you can have external field streams in order for switching, and that too with an analog kind of a switching behavior. So this indicates that there is a possibility that we can use a spintronic bilayer system to make non-volatile memory or devices which have multiple resistive states. Now, subsequently, we basically collaborated with ETH Zurich, and they did experiments. They basically did beamline experiments, and they did XNCD on our samples, and they found out that these different resistive states is because of the switching of the different ferromagnetic domains that we have. And these different ferromagnetic domains arise because the underlying antiferromagnetic domain imprints its domain pattern on the metal. But that's a different study that we did. But what we did was, once when we found this result, then we tried.
Number of what is the age?
So this is the applied electrical current from up to which this loop was swept and then came back. So this is a 12 milliamps.
So depending on the size of your current,
You can basically have the different resistance states. So generally you have a binary method where you sweep current, you go from down to up and then from up to down. But here, when you if you go up to this current and then you make the current zero, you can stabilize your resistance. Then when you go apply the current here and make it zero, you can stabilize your resistance. Like that.
so, I mean, process, I mean, so how is it related to your domain? So
Okay, so what happens is, I think I have this. Okay, so this is basically what happens if you see the system. So this is the XMCD data that was done by ETH, and this is actually the electrical analog of this is Hall resistance versus current, and they did the same measurement by applying a voltage and then measuring the XMCD. So starting from this down configuration, as you apply the currents, you see the different areas they are switching one by one, and that is why you get this multi-level resistance. And what we also found out is these sizes are typically around some hundreds of microns, and that is probably the size is determined by the underlying antiferromagnet itself. This entire antiferro particular domain.
and what is the lower one? I mean, that's XMCD.
Yeah, this is at the different okay
Some
at the
spatial-
different voltages. like 5, 10, minus 5.
Even what is
So here you first saturate the magnetization at one point, let's say here. You apply the different current and then you take the snapshots of the magnetization. And you basically trace out the transport signal in an optical way so that we can see what actually is happening inside.
These domains, magnetic domains.
Yeah, these are magnetic domains.
White region is ferromagnet.
Yeah, the white and black correspond to the ferromagnets with opposite magnetization directions.
This is just a kind of minor loop.
Yeah, we are just measuring this. We're basically measuring the same this result now with taking the image at these several points.
So basically, as you keep increasing current, your magnetization
Yeah.
and then
Yes.
changing back
Yeah.
because of bigger effect.
Yeah. So we are basically doing the same measurement, but now we are just doing it optically so that we can see what is happening inside the sample. But what we did was we thought that okay, because there are multiple resistive states, so why don't we try to actually demonstrate something which is very relevant to the present day research, and that is concerning the fact that how we can make electronic devices mimic brain-like functionality. There is a very active area of research, and there had not been a lot of effort from the Spin-orbitronics side during the time when we did the work. So the logic is because we got a multi-level kind of switching behavior that can basically emulate the working of various components that we have in our brain. And our brain basically has two components. One is a synapse, and the other is a neuron. And these two of them are the fundamental principles of the brain. So we use these big devices to simulate or to show this kind of behavior, which basically emulates the spike timing dependent plasticity (STDP) in our brain. And we also use smaller devices to show this kind of behavior, which is basically the firing of the neurons in our brain. And so what we showed is we have a brain, we can achieve a brain-like computing with a nanosecond regime functionality. So this can be operated with electrical currents. The only problem is these devices consume a power which is around 70 to 80 nanojoules, and our brain operates around femtojoules. So there is still a huge energy mismatch, but still it kind of emulates the functionalities that we have in our brain. But more interestingly, there was one problem that here when we were doing this particular work, we found out that we lose. I just go back. This kind of memristive functionality actually is lost when we start to decrease this device size. And there was a particular critical dimension of around 200 to 300 nanometers, below which this multi-level behavior didn't really show. So then we were trying to reduce this. We were basically trying to see multi-level kind of behavior at much reduced dimensions. And this is the work that was presented last week in MMM. And we have basically come up with a new idea to use a different type of ferromagnet. And this kind of ferromagnets are not actually new because they have been used in the ultra high density magnetic recording for for a long period of time. And we basically have switched these magnets also with spin-orbit torque. And these magnets they have magnetic domains which are around 20 nanometers or 30 nanometers, and they're very well defined magnetic domains. And we made devices of them. This is a device which is around 50 nanometer diameter, as you can see here. And we have shown that with these particular devices, we can even get multi-level kind of behavior down to 80 nanometers, which is probably from the spin-tracking approach, this is the smallest device where you can actually get this multi-level kind of approach. And this is our previous data. So this is the work that we did using platinum manganese, and there this multi-level kind of behavior just vanished at 200 nanometers. But now we can clearly have this kind of behavior at diameter of 80 nanometers. So you can basically claim that we have been more or less successful in showing the world's smallest memristor, or the spintronic memristor at this point.
What is the why does it go away at lower dimension?
For our previous work, what happened was there the switching happened to several different ferromagnetic domains, and the domain size, in our understanding, was probably dictated by the antiferromagnetic domain size below it. The antiferromagnetic domain size was roughly around 200 nanometers. So once we go around the dimension, it just shows the binary switch. But here what happens is, here the domain size is mainly governed by the energy scales inside this particular material, and the domain size here is around 20 nanometers or 30 nanometers. So we can have this multi-level kind of behavior even at much smaller dimensions. We are not restricted with the problems that we have.
Why do you say this anomalous R?
Because the magnetization is out of the plane, so what we are measuring is the anomaly.
But you don't have any antiferromagnetic part.
Sorry?
Don't have any antiferromagnetic part.
No, this is a ferromagnet.
You don't have any bias.
Yeah, actually, the thing is that we tried with that. The problem is that we are not able to get, at this point of time, we are not able to get perpendicular anisotropy with the antiferromagnet below. So for some reason, if we put platinum manganese, this material just falls in the plane or just shows a lot of problems. Some more work needs to be done in this department.
In your previous plot also, you showed more or less similar file R versus R.
Yeah, but then
There you didn't say anomalous, but here you specifically
no,
say
this is I mean, okay, so this is actually the anomalous solid. We measured the because the sample has perpendicular magnetic anisotropy. The thing that we are measuring is the anomalous solid, and I think which I just said it's all, but yeah, this is the basically the anomalous.
it's anomalous.
Yeah.
Yes. This is a tricky thing. It's a very specific thing. I mean, after topology involved into that, all can be set to various networks.
Yeah.
How do you know that this is actually all coming from that very curvature?
So this is a ferromagnetic system. This is a ferromagnetic system. So uh, and this is a ferromagnetic system. So we basically know that the Hall resistance is contributing is proportional to the Z component of the magnetization that we expect for the anomalous Hall, and that is what we are measuring. So
Okay, well, that's fine.
So in here you don't have any contribution from any convention also. Anything. You have a magnetic component.
yes,
Yes.
yes.
That you also contribute.
You mean for the switching, or
No, the anomalous one.
well, we didn't in this research we didn't quantify the origin of the anomalous Hall. So
I mean, you just say it's because of ferromagnet.
yeah, so in a ferromagnet, the Hall resistance is proportional to the Z component of the magnetization.
That is true, but
Yeah.
is this the general phenomenon that all ferromagnet is not
When you have a
Yeah, all
magnetization,
ferromagnetic will show anomalous. But origin of anomalous may be intrinsic,
intrinsic or
may be
extrinsic,
extrinsic. You different kind.
that is what I'm not telling because we didn't clarify the intrinsic or the extrinsic.
Yeah. Origin may be different,
Different.
but all ferromagnets will show. Antiferromagnet may show
Some of them.
Yeah, but
For that, we have to do this RXH dependent.
Yeah.
That's something. Usually,
So this actually just
no.
Yeah, I think that
so this actually brings me to the end of the first part of the talk. I'm already running out of time, I guess.
So, those that have
So
learned-
maybe I will, I don't know, maybe I'll come back a later time. Or I can just show you some of the very briefly what we are doing at SIMP. So I joined, just skip through all of this. I've been working on fermions as well, moving them with electrical currents. Okay, so just to give you an idea, so I joined SIMP in August, and we have a good growth facility at SIT, and we are using we have a magnetron sputtering where we can basically grow thin films. We have 4 magnetron sources and an EV incorporator as well with that. So we have optimized that system, and also we have a pulse laser propulsion system on which we can grow oxide thin films. So currently, I'm basically trying to work in 2 directions. This is, some very recent work that we have started. We have started to work on orbitronics, where we try to basically convert the orbital angular momentum into spin current. And we have been able to optimize this very beautiful thin films of gadolinium on different on silicon substrates with various different underlayers. And also, we are working with 2D materials as well, and these devices were not made in SINP, but we hope that collaborating with some of my friends here and other places, we'll be able to make these devices. And this is another result that is currently under our review. What we found out is we are working with this material, which is very well known 2D ferromagnet now, iron, germanium, tellurium. Previously, the last 2 years, we were working on the bulk, we were doping them, but then we decided to make devices out of it. And we found out that in the bulk, this material has a very interesting ground state, which hosts this topologically protected spin textures, which are called fermions. And it was not only shown by us, but also other people as well. And we basically then showed that you can also use a magnetotransport way to get the signatures of the existence of these textures. So once we exfoliated these materials and made devices out of it, these are roughly 30 nanometers in the, on the size of the flakes. So we were able to get a very good, signatures of anomalous Hall effect from the systems, and we saw that even down to this 30 nanometer, where theoretically it is predicted to be a single domain. In our case, we were still getting signatures of the existence of this spin texture. And this is something which is very interesting. We don't know at this stage why we are getting this, but we are in discussion with some of our theorists who basically have told us that it could be something different, may not be fermions but something. So these are the kind of works that I have started at SIMP. So this signature, when you apply the magnetic field in the plane and you measure the transverse resistance, we previously showed that if this is a Stoner-Woolford magnet, then it should not show this kind of a behavior. But here what happens is it goes up and shows this peak and then comes down. And we showed previously that this is a signature of the existence of this spin texture in the system.
Y-axis RX1.
Yeah, these two are the same axis. But here the magnetic field is out of the plane, and here the magnetic field is in. That is only. And we also, in our previous work, we also compared this data with the magneto-optical imaging. So when you have this kind, how do you know that there is a spin texture involved? So we did this concomitant measurement where we measured the Hall and also we measured the magneto-optic at some particular magnetic fields, and then we see that it kind of matches with the image that there is a existence of texture, spin texture.
But you apply electric field and magnetic field in the same direction.
Yeah, this current density is very small. So the current density, in our understanding, is not causing any effect on the magnetization.
But the geometry of this device is like you are applying
Electrical current.
X-axis.
Yeah, along the
And
x-axis.
the magnetic field is also along X-axis.
Yeah, in this case, the magnetic field is also along the x-axis.
And you are measuring the voltage.
We are measuring the Hall voltage.
What that should give you?
We saw that in this case, that gives us that actually bears the signature of this topological texture. That's what we showed last year.
You mean E dot B term?
Sorry?
You mean E dot B term? There will be E dot B.
Yeah.
I dot B term.
Yeah.
That will give rise to some signature in the Hall.
Uh,
I'm saying why do you expect it's
He says fermion.
I don't know. Whatever may be electric field and not perpendicular to magnetic field.
yeah.
Usual Hall, they are cross.
Yes. Yes. But here, in our case, when we compare the transport and the imaging part, then we see that these signatures arise from the existence of the textures.
Yeah.
But the anisotropic magnetic resistance doesn't, like for our case, just doesn't only explain the behavior that we see.
There is no other source of so high and
Yeah.
what can price. Like,
Yeah.
this is only thing that you can here. So for magnetic anisotropy, which is
No, but we also have the texture, right?
that is what I'm talking.
Yeah.
This texture is giving rise to the anisotropy.
So the magnetic anisotropy.
Yeah.
No, actually, what the signal you are measuring, what it is, not resistivity, not neither resistivity nor it is a all in common sense.
Yeah. 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 Yeah.
Mm,
Yes, a
If it
component of magnetization in that direction. So,
Yeah. Actually, it's
So if you reverse the current, like
yeah.
current in the other direction, what do you get? You get the same speed as the same.
Like in this direction,
Yes.
we didn't check that.
no, actually, if it is due to simple resistive part, then it would be symmetry where one can reverse the magnetic field, then it will usually cancel.
that was
Spin
anisotropic.
texture and also reversible.
Huh?
Spin texture and also
Okay,
will be
yeah.
topologically protected.
Yeah.
If it is so, then another thing.
We had seen that kind of things. When we applied the UK, we had seen solar systems. In fact, Bainey also showed one of his papers.
But that is
Topological.
very
Yeah, it has some anisotropy and the
Yeah,
magnetization
that's
is not
anisotropy
zero. So
could-
it has
yeah,
some
some
component of
anisotropy.
magnetization.
And it goes to zero at after 4 Tesla.
Yeah, it's
Sorry?
more anisotropic if it is like going.
No, it goes to zero. The signal goes to zero.
So what we understand, what I thought is that basically the spin textures are annihilated as an increase in energy.
It can be at high field, if clearing the
Yeah, we are moving
the
entirely.
phenomena.
Yeah,
It will be same. High field when we apply both the external field will
Yeah.
destroy.
That is a uniform.
More like
Yeah.
cardinal Hall effect. And you are
But we tried, we wanted to see, but of course, these types of it's not possible to visualize it with magnetometric effect. So, we are now considering that we are discussing with our friends and here is what we talk. So yeah, so this is all that I have to show. I'm looking for, I had a very beautiful discussion with many of you here. I'm looking for active collaborations for device application because we can grow films in this angle. It would be wonderful to be able to work together and you know, either on the fab part or on the measurement part.
In this case, your rho XX,
Yeah.
is it metallic type or it's an insulating? Because rho XY is
This is low XY. This system is a metallic.
still metallic.
Yeah.
In this thickness.
Yeah, 30 nanometer is still metallic.
But your RXY is increasing with temperature. Decreasing
Decreasing.
with increasing
With
temperature.
increasing.
Which normally is not
Yeah.
the case.
No, the RXY decreases with increasing temperature.
Yeah, that is expected.
That is expected
It
because
will
of magnetic.
disappear above ferromagnetic value.
Yeah, this 200 is roughly the.
Behaves like rho XX.
So you are saying because your magnetization is going down.
So the unit temperature is roughly
Magnetization is
200.
Magnetization is going down.
So magnetic
activity is
phenomena weaken in
the
the
perpendicular direction.
So the only thing that we saw that the metallicity is still preserved, but the ordering temperature, the Curie temperature is dropped down. The bulk was around 225 Kelvin, but in the thin flakes it's roughly around 200 or 195.
meaning
Yeah, exactly. Okay. Okay, so yeah, that's all that I had to show. So thank you very much.
There are a lot of questions. I don't know if
Students.
any more questions?
How thick was your active plate?
This is around 30 nanometers. This is the AFL image. It's roughly around 30.
Still, we have like a bulk.
Yeah.
Yes, but according to literature, around this thickness, you should have a single domain. It should behave like a single domain magnet. So that is what was actually the original idea. Then
It doesn't depend on the lateral dimension, only on the thickness, the domain size.
that was what was shown in like when they made this really thin breaks, and
It should also depend on the lateral size. of what we
yes,
have.
but I think the dipole interaction is maybe what more than so the dipole interaction is changing when you are reducing thickness, and then it becomes single domain. When the
You
anisotropic,
think the full, I mean, you have a nano shape, I mean, or one
no,
layer,
not a
mono.
mono.
I mean, if you even if you isolate one mono layer or whatever, I don't think it would be single domain. Right? I mean, there should be a critical size.
Here comes is a critical size, but roughly of these dimensions, which is around like 5 microns. Most of the experiments were done on this kind of stuff.
You know what the typical domain size is?
No, but
In
this
bulk?
we don't know. In bulk, actually, the bulk has a very. I mean, I don't know. I can show you. Maybe yes, okay. I can show you later. So the bulk ground state is actually very confusing. So this is a uniaxial magnet. So if we if we try to image the bulk, what we saw is there is a stripe domain, alternating up and down domain, and embedded among them, there are some texture kind of stuff. Now the problem is if we see the theory of magnetic domains, then people have shown that in materials with high magnetic anisotropy, for this case the anisotropy constant is roughly around at low 10 Kelvin is roughly around 10 × 6 joules per meter cube. You can have this pinch stop domain embedded within the uniaxial thing. But some people say that these are not pinch stop domains, but these are sub. So that is a very difficult situation right now with this 2D magnets.
Maybe a centrosymmetric.
This is centrosymmetric. That you don't have any symmetry breaking interactions here. The BMI other things.
And this compound is under debate. I don't think anyone understands that.
Now that is why
Any of
we
this.
wanted to study what is done.
Okay, if there are no more further questions, we thank
Thank you.
Mr. for very interesting. Thank you for a lot of questions.